My name is Hongyao. I'm a PhD student at Harvard. This is joint work with Reshef, who is now at Technion, and David Parks. So I'm going to talk about social choice with payments, which is also usually referred to as the provision of public good. So we answer the question of to which extent can people's utilities deviate from quasi-linearity? Will there still be non-dictatorial mechanisms that are strategy-proof? So the social choice mechanism that we study selects one alternative outside of a finite set of options. For example, the engineering school at Harvard is building a new building across the river, and we want to select one chair to fill the lobby area. One idea is to ask the different department heads to vote. We know that with two alternatives, the plurality rule is strategy-proof. But with three or more alternatives, the Gilbert-Satterthwaite theorem says that there is no good solution. Like with unrestricted preferences, any mechanism that's strategy-proof and onto must be dictatorial. So one may use payment to get around this. And social choice with payments is very well understood if we assume quasi-linearity, which means that an agent's utility is equal to her value for the selected alternative minus her payment. So we know that VCG is strategy-proof and maximizes social welfare. We also know the Roberts theorem characterizes affine maximizers of all the agent's values as the only implementable social choice rules. But if we think about these two settings, in voting, once an alternative is selected, the mechanism has no power at all to affect an agent's utility. And with this quasi-linear setting, we're kind of assuming a lot of structure and a lot of understanding on how people think about money. So we study the non-quasi-linear setting and try to understand what if the mechanism does not fully understand how agents think about money. So this is what utility looks like in the quasi-linear world, utility as a function of payments. But in reality, there is often budget constraints or wealth effect and risk preferences. In these cases, money kind of becomes more expensive as people are spending more of it. So the utility functions are concave. I don't have time to get into the details of this setting, but in certain scenarios, if we consider people only make the payment if they made some bad decision or take some bad action in the future, then having a larger payment reduces the probability that they actually take the bad action, and this reduces the slope, so the utility functions are convex. One may also imagine, say, the school give the department head some fake money or points to express their preferences. In this case, I still prefer paying less points because I'll save my points to decide, for example, where the kitchen should locate. But it's unlikely that utility as a function of points is going to be quasi-linear. Very little is understood about social choice with non-quasi-linear utilities in the literature. The closest paper is our work in Ithaca from 2 years ago. So it is an impossibility result of non-dictatorial and strategy-proof mechanisms, but it assumes like the most general non-quasi-linear utility domain. So we assume like agents' preferences can be any decreasing function of payments. So so one may be interested in, like, what if people have less richness in the non-quasi-linearity in their utilities? So this leaves a big gap in the understanding. So this paper, we provide a tight characterization of the maximum non-quasi-linear utility domain, where there exist non-dictatorial mechanisms that have these 5 properties. So we require incentive compatibility and deterministic mechanisms. P3 on 2 only requires that every alternative can be selected, and we don't require all the payment schedule is reachable. P4 IR requires that no agent should be worse off than a scenario where her worst alternative at 0 payment is selected, and she doesn't make any payment. So people don't have incentives to walk away from participating. No subsidy, P5, requires that the mechanism does not make a positive transfer to any agent. So we call this maximal utility domain that we identified as the largest parallel domain. I'm going to define it on the next slide, but intuitively, it kind of requires that an agent's utility for money depends only on her utility level, like how happy the agent is. And this should be irrespective of which alternative is selected or how much payment she's paying. So within the parallel domain, we can generalize the weighted VCG mechanism. We show this has all these good properties. We also characterize all the implementable social choice rules, so we generalize Roberts theorem. But if we step outside of the parallel domain, immediately we have dictatorship under these 5 properties. We also consider a slightly richer non-quasi-linear utility domain, which still deviates very minimally from quasi-linearity, but we will have a Gilbert-Satterthwaite style impossibility result with only DSIC deterministic and onto. Okay, now I'm going to define the parallel domain. So the horizontal axis is payment, vertical axis is utility. This is an agent's utility function for alternative A as function of how much she pays. And we consider 2 more alternatives. There's B and there's C, and they look weird. So alternative C is this agent's worst alternative at 0 payment. And this dotted line is the utility level for that worst alternative at 0 payment. So what parallel domain requires is that in the range where payments is non-negative and where utility is above this dotted line, the utility functions for the different alternatives must be horizontal shifts of each other. So what does it mean is that if we cut this, like the shaded area horizontally, the length of these arrows are all equal. So our eyes really don't want to believe that they have the same shape, but you should believe me, they really have the same shape. Okay, so immediately as a result, we know that if we cut these curves horizontally, the slopes for the different curves must be equal, which means like the DC utility for money depends on the utility level. We call the set of all types that has this property the largest parallel domain, and we don't denote it as U parallel. It's obvious that quasi-linear domain is a subset of the parallel domain, and there are non-quasi-linear types that are parallel as well. What is very interesting about these types is that the willingness to pay plays an important role. So here we define the willingness to pay for an agent for an alternative as the crossing point of this utility function with the lowest utility at 0 payment. So here's the willingness to pay for alternative B, for alternative A, and then the willingness to pay for C is 0. What is interesting is that the willingness to pay for parallel types almost plays the roles of values for quasi-linear types. So the length of the arrows is equal to the difference in the willingness to pay for the 2 alternatives. And we can see that an agent prefers alternative A if and only if the additional amount that she is charged for A is smaller than the additional willingness to pay that she has for A in comparison to B or C. And if we rewrite it, we can see that the shape of the utility function actually doesn't matter. The only thing that matters for which alternative does an agent prefer is the difference between the willingness to pay and the value. So this lemma is very useful. First, we prove our positive result. A generalized weighted VCG mechanism is parametrized by coefficients for agents and constant for alternatives. So big N is a set of agents, and the big A is a set of alternatives. Basically, just replace all the values in the VCG mechanism by the willingness to pay. We select an alternative that maximizes this affine function of willingness to pay. For an agent who have a 0 coefficient, who doesn't affect outcome at all, the agent doesn't pay anything. For an agent who does affect the outcome, we charge the reweighted version of the externality that she imposes on the rest of the economy, computed in terms of willingness to pay. So we first prove that this mechanism has all the properties that we want. Everything else is very easy. For DSIC, we first observe that the prices are agent independent. So it means that regardless of what I report, as long as alternative A is selected, what I pay for A does not depend on my own report. So it's a function of the report of the rest of the agent, U minus I. And then we show that the mechanism is agent maximizing. So it actually chooses an alternative that's best for everyone, given all these agent-independent prices. Here we use the lemma from 2 slides ago. So agent independence and agent maximization are known to be necessary and sufficient for incentive compatibility for quasi-linear world, and it's very easy to generalize this, like for the non-quasi-linear world. We also provide this generalized characterization result. Basically, the affine functions of willingness to pay are the only thing that can be implemented. Similar to the result in quasi-linear utilities, we require 3 or more alternatives. For the Roberts theorem for quasi-linear utility, it requires the unrestricted domain, which assumes that the values can take any real numbers. So here we require an unrestricted domain in terms of willingness to pay. So willingness to pay have to be able to take any numbers. And in this case, these are the only thing that's implementable. A little bit of intuition of how this is proved. So we first generalize weak monotonicity to non-quasi-linear utilities, so in terms of willingness to pay. What this means is that regardless of what the other people reported, if I'm able to change the outcome from B to A, no, from A to B by reporting U prime instead of U, then the amount that I gain for alternative B by reporting U prime must be larger than the amount of willingness to pay that I gain for alternative A. So it's known to be a necessary condition for incentive compatibility, and we show that it's also the case for non-quasi-linear domain. And this is the main result that's driving this characterization result. So okay, now I'm going to use this characterization result to prove our impossibility theorems. So first, we generalize the concept of a dictatorship to social choice with money. So we say that the mechanism is a fixed price dictatorship if there is a set of fixed prices, one for each alternative, and there is a dictator, I star. The outcome of the mechanism is this dictator chooses what she likes the most from the set of alternatives given these prices and pay the corresponding price. So here's our result. With 3 or more alternatives and with a utility domain such that for every agent, her utility domain is at least as big as a unrestricted parallel domain. And also for n-1 of them, they have to have at least one type that's outside of the parallel domain. So if we have these conditions, then any mechanism that is DSIC, deterministic onto individually rational, and does not subsidize the agents, must be fixed price dictatorships. If we strengthen this result a little bit and require Pareto efficiency instead of onto, then we only need a single agent to have a single type that's outside of the parallel domain. And moreover, these mechanisms have to be full dictatorships because we can't charge the dictator anything without violating Pareto efficiency. So first, these results actually require very little deviation from the quasi-linear domain. For example, if we have 2 agents, it's sufficient if the first agent just have the quasi-linear domain as her utility domain, and the second agent has a quasi-linear domain plus this single type that's like looking like that. So intuition for how we prove this. First, suppose we're given a mechanism that have the properties P1 through P5 on this utility domain, it must also have these properties on the parallel subdomain of the original utility domain. And we can apply the generalized Roberts to show that on this parallel subdomain, it has to be an affine maximizer. So what this does is it fully pins down the agent-independent prices that one agent can see if the rest of the agents report their types that are parallel. So with this, we can show that if we take any 2 agents, one of them has to have a non-parallel type according to our assumptions. And we can show that it can't be the case that both of them have a non-zero coefficient. Otherwise, we have a contradiction. So there has to be only one agent that has a non-zero coefficient. Let's call her I star. And then we can show that her agent-independent prices cannot change regardless of the other people report, even if the other people's reports are non-parallel. So this is proof by induction. It's pretty intricate, but this is a high-level idea. Okay. This is our other result without requiring IR or no subsidy. It requires a utility domain, which we call a linear domain with two slopes. So what this has is, so for each agent, there are two slopes. There's alpha and beta. They can be arbitrarily close, but they have to be different. Then for any type and for any alternative, my utility is linear, and you can either take the alpha slope or the beta slope. We prove that in this domain, anything that's deterministic and onto and strategy proof must be a dictatorship. It's OK if all the agents have the same alpha and same beta, and the alpha and beta can be known to the mechanism designer, as long as the mechanism designer does not know for each specific agent and each alternative what the slope looks like. OK, to wrap up, we provide a tight characterization of the largest utility domain within which we have reasonable mechanisms with good properties. So future directions, one thing that's interesting is to consider social choice mechanisms with solution concepts weaker than DSIC or with randomization. It's also interesting to think about other problems with non-quasi-linear utilities, like for example, assignment with multiple demands. So there are known impossibility results with very rich non-quasi-linear domains, but there might be opportunity to step outside of the parallel domain but still have good good mechanisms. Thank you very much. The paper is on arXiv.
So the impossibility theorem shows that the parallel domain is maximal. You can't make it bigger without having impossibility. Why is it the maximal domain? Couldn't there be incomparable domains that also?
So with the 5 conditions that we assumed, it is the maximal domain. Like the utility functions when the payments is negative or when the utility level is too low actually is irrelevant. That's because the range that we care about is the only relevant thing for mechanisms that's IR and no subsidy. So if we relax one of those two, there might be other mechanisms that satisfy the first 3. Yeah. Yes.
It would be interesting if there are some restrictions even without any payments, right? Like single peak preferences where we can get strategy proofness.
Mm-hmm.
So presumably if you add payments like this to single peak preferences, you can do even more. Or maybe we can even relax single peak preferences if we
allow payments
with some restriction. Have you thought about those things at all?
Not much, because if we go beyond like no payments, then like how like defining single peakness in terms of like utility like as a function of like possible payments, it's just a little bit a bit tricky to think about this. Yeah, we haven't thought much, but we'll think more. Questions? Okay.